speaker is Stavros Papadakis, who will talk about polynomial and normalization. Stavros?
Thank you, Vasiliki. This is the main subject of the present talk, which will be application of Custin-Miller unprojection, which you heard about it in the previous talks. 2-3 things: to stellar subdivisions of simplicial complexes, to cyclic polytopes, and the last and maybe most interesting, to the degree normalization, also known as volume normalization, of the Artinian reductions of a Gorenstein graded algebra. We will say more about number 1 and number 3, and only a small introduction to number 2. Let me remind you that about the history of Custin-Miller unprojection. The first paper was in 1983 by Custin and Miller, and then Reed and developed a theory, and you can consider it as a method for constructing and analyzing complicated Gorenstein rings in terms of simpler ones. There is Custin-Miller unprojection is a specific part of what is called more general unprojection theory, which is due to Miles Reed and collaborators. And one can consider the unprojection theory in general as an algebraic counterpart of certain constructions in birational geometry. Custin-Miller is the unprojection that has been studied more and so far has found more applications. So now we introduce again, we recall the setting of Custin-Miller unprojection. You start with two ideals, homogeneous ideals in a polynomial ring. And you consider the ideal J divided by I, which will just be called J of the ideal S. So the important initial data is S, which is a quotient of a polynomial ring by homogeneous ideal, and an ideal J of S. What do you want to assume? The important assumptions are these three ones. S, which means R over I, R over J Gorenstein, and J is a codimension 1 ideal of S. This is like the definition of Custin-Miller unprojection pair. You have an ideal of a Gorenstein ring, which is codimension 1, and the quotient is Gorenstein. As was demonstrated in a previous talk by Basso, duality theory gives us a short exact sequence connecting the S module of homomorphism from J to S to the rings, to the cyclic modules S and S divided by J. One can say that the last map is like an algebraic generalization of the Poincaré residue map in complex geometry. Because of this short exact sequence, the module on the middle, the home module, which is the important module, can be generated by two elements. One of them is the inclusion, which comes from the map from S to home. And the other is a homomorphism phi from J to S, which is the important object for everything, for the theory. And it is like can be considered like roughly speaking, like a rational function with unique pole on B of J. This is like a kind of interpretation of phi. As was mentioned in the previous talk, Miles-Rich defined from this, using phi, the Custom-Miller unprojection ring of the pair J subset S, or sometimes we write it pair J comma S, and is defined as in the slide. An interpretation of it is that it is the unprojection ring corresponds in some sense to the graph of the homomorphism phi from J to S. This was just a reminder from a short introduction to Custom-Miller unprojection, because, and now we go to the applications of it. Assume we have a simplicial complex and the face of it. As it is well known, you can do the stellar subdivision of D with respect to sigma and get a new simplicial complex with the same, so to speak, geometric underlying space, topological space. For example, if we have the two simplex with vertices 1, 2, 3, and the face is 1, 2, we can do the subdivision and get a simplicial complex with two facets. While if we consider the face 1, 2, 3 of the simplicial complex, we get a simplicial complex with three facets. Another example is that if we have the boundary of the endpoint and we have a one face of D, then B sigma is the boundary of the n plus, sorry, of the n with one more vertex. Now we will introduce the class of Gorenstein star simplicial complexes. And we say that the simplicial complex is Gorenstein star over a field if, first of all, the face ring KD is Gorenstein, and moreover, for every vertex V, there exists a phase sigma such that the union is not a phase of D. This means that D is not a cone over any of its vertices. Gorenstein star class is better behaving than just assuming that K be Gorenstein. For example, every link and stellar subdivision of Gorenstein star is again Gorenstein star, which is not true if we just assume that the ring is Gorenstein. The first remark, which is that every simplicial sphere has this property, is Gorenstein star. And the second example tells us that if we have a simplex considered as a simplicial complex, we have the following properties. The phase ring is Gorenstein. It is even a polynomial ring, but clearly the second condition of the definition of Gorenstein star is not fulfilled. So a simplex is not Gorenstein star. Now we go to the following question. Assume we have a phase of a simplicial complex D and we do the stellar subdivision. We have two phase rings. The phase ring over D, of D, and the phase ring of the stellar subdivision. The question is how the two phase rings are related in a structural way. And the answer is that if we have the further assumption that D is a Gorenstein star simplicial complex, then there is a general method that I will describe in the next slides, which is like a kind of tautological construction to use Custin-Miller unprojection to go from the phase ring of K of D to the phase ring of D sigma. In more detail, we define S to be the polynomial ring in one variable Z over the phase ring of D. And we define the ideal J of S as in the slide. J, as was mentioned, clearly is related to the link of sigma in D. So the important, we define a ring S, a Gorenstein ring S, and a homogeneous ideal J of S. The theorem is the following. First of all, the ideal J is a codimension 1 ideal of S with the quotient being Gorenstein. Then we denote by JS the Custin-Miller unprojection ring of the pair J subset S. The important conclusions are that Z is a regular element of this new ring, the unprojection ring. And regular element means that the multiplication by it is injective. And moreover, if we divide by this element, we take the quotient ring, this is in a sense naturally isomorphic to the stellar subdivision of d sigma, of d with respect to sigma, to the phase ring of the stellar subdivision. So in some sense, this unprojection ring plays the role of a bridge connecting the original KD and the phase ring of the stellar. We will do an example now. And this is the example of the stellar subdivisions of the boundary of the trigon with respect to a facet. We write down the phase ring, the Stanley-Reisner ring of D. We do the construction in the statement of the theorem, so it means we define S and J, this pair of a ring and an codimensional ideal. And then one can compute that the projection is this ring, which we remark is not a monomial ring anymore. And this ring divided by the variable z is the phase ring of the stellar subdivision. So as we said before, this ring, which is not monomial, plays kind of role of bridge between the rings of the Stanley-Reisner ring of D and D sigma. This theorem has been used for a number of purposes, like studying the Stanley-Reisner rings of the structure of Stanley-Reisner rings of stacked polytopes, for giving Betty bounds for the stellar subdivisions of a simplex. Is there any question?
It seems I'm not.
Okay, I will now present, I will just say a few things about the application of Kustig-Miller unprojection to cyclic polytopes. Let me first remind you that the cyclic polytope, the definition of the cyclic polytope, we consider the moment curve from R to RD. We take M distinct real numbers, and we take the convex hull of the images of them. This way, it is well known that we get a simplicial polytope, which depends on two parameters, D, the dimension of the space we are, and M, the number of points we took. We denote by delta D comma M its boundary simplicial complex. cyclic polytopes are useful in combinatorics for a number of things, but the remark we want to make now is the following, that one can use Custin-Miller projection to express the phase rings of the delta dn plus 1 in terms of the phase rings of delta d comma m and delta d minus 2 m minus 1. So in this way, one can build the phase ring of delta in an inductive way. For example, this allows us to construct, using the Custin-Miller complex construction, the minimal graded tree resolution of delta dn. We remark that we are not accepting very small values of d like 2. In all other cases, we are not having a stellar subdivision relation. So this is not in the previous, it's not covered by the stellar subdivision result. I mean, and anyone who is interested can look the details on the published paper. I do not want to say more about it. And now we go to the main topic of the present talk, which is application of Custin-Miller projection to degree volume normalization. This was briefly mentioned in Karim's talk, and now I will give more details and more precise statements. First of all, we recall the following definition of the generic Artinian reduction. What is important is if we have S, the K algebra S, we can do this construction, which adds new variables, does a field extension, which is a purely transcendental field extension, and defines A. This is like a natural constructions because we don't make any choice. Aij are new in independent variables, and that's useful. First, it's useful that we don't make a choice, and second, it's useful that they are as independent as possible. The question that the rest of the talk will be about is the following. Assume we do the generic Artinian reduction of S. This is a finite dimensional graded K vector space. A is a finite dimensional graded vector space. So it has a top degree. Let's call it R. We assume that S is Gorenstein. This assumption implies that the top degree, which is the circle, is a one-dimensional E-vector space. That's very well known and classical. Now we put the question, that we repeat the question that we did also in a previous talk. Can we find an isomorphism from the top degree to E, which is preferable or canonical? And the question is, what does it mean, preferable? So in the next slides, I will try to motivate this question. Because it seems that this is a useful question. And let's see why. So we go to the study of simplicial spheres and the second proof of G conjecture by Papadakis and myself. So we have a field of characteristic 2 and a simplicial sphere. It's a general fact that the top degree of R of the generic of any Artinian reduction and of the generic Artinian reduction is equal to T. Then a first proposition is the following, that assume we have two facets of D, then on the Artinian reduction on A, the bracket sigma x sigma is equal to bracket T x T. And moreover, this bracket sigma x sigma is a basis of AR. Our motivation was to compute because we wanted to show to study anisotropy. And anisotropy is u squared not equal to 0. So we wanted to put a basis. We needed to put a basis in AR. And we looked if there was a natural basis. And this equality suggested to us that something interesting is going on. Of course, x sigma is like before, and bracket sigma is the, as was mentioned in some previous talks, is the determinant of the submatrix of the coefficients Aij by keeping columns J with J in sigma. And this is just like an elementary proposition that comes from Gauss elimination. And moreover, it holds in greater generality for pseudomanifolds, that this equality. And if it's orientable, we have also that it's a basis. Okay, so this means, as was mentioned a number of times in previous talks by Vasiliki and Karim, that there exists a unique E-vector space isomorphism, denoted originally psi or gig or vol. But on this talk, we will use the notation psi from the top degree of the Artinian reduction to the field, which on each facet, on each x sigma, psi of x sigma is 1 over bracket sigma. And this is called for all facets sigma of t. Now we make the remark that the differential identities that were used in the proof of generic anisotropy hold for this isomorphism psi only. So perhaps it makes sense to consider psi as the preferable canonical isomorphism. Moreover, with respect to this psi, we get very nice formulas for, the psi of a monomial, for example, is as simple as possible if we use this psi. Let me give you an example that was also mentioned in previous presentation. We consider the boundary of the M-gon with consecutive vertices 1, 2, up to M. And we start to compute. We are interested on monomials of degree 2. So psi, and of course, psi of xi, I plus 1 is a fast set. And by the definition of psi, we have this formula. Now we are interested on the squares, because anisotropy is related to squares. And one can easily prove that, for example, psi of x2 square is given by this nice combinatorial, this nice formula. So our experience says that somehow this is using this psi and is like a nice representation of things in the Stanley-Reisner, in the Artinian reduction of the Stanley-Reisner rings in terms of rational functions in the Aij. And it has certain nice properties. For example, on the M-gon, 2 is connected only to 1 and 3. And the only indices that appear here are 1, 2, 3. But there are even better and in the things that were mentioned without details in the talk of Karim and also in the presentation of talk of Vasiliki, given explicitly there with computer code. So we have what we now call Parseval identities. And this is the example of Parseval identities in the one-dimensional case. What is the format? It expresses psi of a monomial in terms of squares of psi. I emphasize we are in characteristic 2. And the coefficients are really simple polynomials in the Aij. So we have for all line, the first and the second Parseval identities. Of course, we make the convention that n plus 1 is 1 and 1 minus 1 equals m. So we work on the indices 1 to n cyclically. And these identities have corresponding equivalent differential identities, like the one written below. I emphasize that we prove this identities for psi. Caru and Xiao proved some more identities about psi that we conjecture. And these identities are really strong because if we have them, they imply the G conjecture for simplicial spheres using some rather elementary additional arguments that were sketched yesterday by Karim. Also, we gave the name partial identities because to our mind, it looks like a bit like some formulas of harmonic analysis, but in some sense, because we express something in terms of squares. I don't know. I mean, these are some examples of partial identities and differential identities. Are there any questions?
It seems that no.
So this is under the assumption that we are in a simplicial sphere. And so we can define, give this definition, what is the volume polynomial, which is just a way to encode this information. So the volume polynomial of a simplicial sphere is just the sum u, psi of u times u, with u over all monomials. Sorry. So this is the volume polynomial. Now we go to the next question. Okay, for Stanley-Rice the rings of simplicial spheres or pseudomanifolds, you have this natural definition of psi. What about more general? Can you assume you have a generic reduction of a Gorenstein graded algebra of this form? The rest of the talk, which is ongoing work, is to propose a suggestion, or maybe to suggest how to define, using Custin-Miller projection, a preferable canonical isomorphism psi from the top degree of R, A to E, and do it completely algebraically, I mean, with no combinatorics involved. So our aim is to try to use Custin-Miller projection to define psi. Now we introduce a variation of the generic Archimedean reduction, which we call generic polynomial reduction. Again, we start with a field, any field, not necessarily infinite or characteristic 2. S is a polynomial is the quotient of the polynomial ring by homogeneous idea. And we assume that S has current dimension D greater or equal to 1. We do a variation of Artinian reduction, which of generic Artinian reduction. We consider new variables. We consider a phi as before, but now we do this polynomial reduction. We do this polynomial definition. Before Aij were invertible. Now they are not. That's the only difference. So on Vita, Aij are no longer invertible. That's why we call it generic polynomial reduction. Our aim is to use the generic polynomial reduction to find psi for A, for the generic Artinian reduction. So we would use generic polynomial reduction as a tool for that. Let's see how we do it. We assume that S is Gorenstein and Z is a new variable. We define the polynomial ring over Vita in the new variable Z, and we consider the ideal J, which is the variables xi, all of them, together with Z. Now, J is an ideal of C, such that C is Gorenstein, J is codimension 1, and the quotient is Gorenstein. That they are more or less obvious. So this means this pair, J, C, satisfy the Custin-Miller unprojection assumptions, which hence, as we said in the beginning and was proven by Vasiliki in the previous talk, there is a short exact sequence of C modules. One can prove that there exists a W in B, not involving Z, such that the homomorphism from J to C, which is uniquely specified by Z maps to W, together with the inclusion, generate home, a C module. Again, the important player, the important data is in home, and this home is generated by the inclusion together with FW for a certain W in Vita. So we use again Miles-Ridge philosophy that that you should look for the generators of this home, and they are important. Okay, so we have a W. So there is a W in Vita with the property as in the statement, as in the slide. What do we do with this W? And now we have this suggestion for the definition of psi. We denote by A the generic Artinian reduction of S, which is an E algebra. And by R, the top degree of A. One, we can show that the class of W in A has the right degree, A is in AR, and moreover is non-zero. So the class of W in AR is a basis of this one-dimensional E vector space. What we do, we suggest conjecture that the preferable / canonical isomorphism psi from AR to E should be the one which is uniquely specified by the condition that W maps to 1, the field. What is the evidence for this suggestion? The first piece of evidence is that actually in the case of simplicial spheres, we can actually prove that up to sign, and characteristic to the sign is always 1, so it doesn't matter. We have the following equality in B. The important basis bracket sigma x sigma that we used before to define psi is equal to W. So this is for every simplicial sphere and every field. So this is one of our motivations for it. A second motivation comes from a large number of experimentations with Macaulay 2 for other kinds of ideals I. And let's see this, what we call cut example, without having any good reason to name it like that. So here we thought the following: okay, if this is a good definition, try to apply it to an ideal that it's prime, and apparently seems to have very little to do with combinatorics, especially with monomials, and see what you can get. So we start with a field of 2 elements, K, and we consider this ideal I. Which is a homogeneous ideal, clearly a complete intersection with dimension 2 ideal. Then, what is interesting is this ideal is prime ideal. So it is a prime complete intersection with dimension 2 ideal. And the Hilbert function of the A, so the Hilbert function of any Artinian reduction of R divided by I is 1, 2, 1, and then 0. As it is, we used the Custin-Miller projection as described above. To define an isomorphism from A2, this means the second graded part of A, to the field is, as was mentioned before, is just K of the field of rational functions in all Aij. Then we actually got that this Parseval identity for the cut, which says that for all U elements in A1, in this two-dimensional vector space, we have this identity. Psi of U square is a polynomial times psi U x1 square plus a polynomial psi U x2 square plus a polynomial psi 0, but it's okay, psi U x3 square plus a polynomial psi U x4 square. So in some sense, this is a Parseval identity for the generic Artinian reduction of the cut for squares. And even though we have a 0 here, it is easy to see it by differentiations, and because the space is two-dimensional, and here we have x1, x2, x3, x4, that this Parseval identity implies that R divided by I is generically anisotropic. Any questions?
No.
Okay, so let's see the references. This the first paper with Karim and Vasiliki is used these ideas and plus further techniques for Lefset's properties for pseudomanifolds and cycles. The second paper is the one already mentioned for cyclic polytopes. The third paper is the stellar subdivisions paper, which was the first part of the present talk. The Custin and Miller paper is the original where Custin and Miller and projection appeared for the first time. The 2020 paper contains the second proof of G conjecture for simplicial spheres. The joint paper with Miles Reed contains the formulation of unprojection as was presented on this talk and in the previous ones. Custin and Miller had an equivalent but different construction using chain maps between complexes, between chain complexes. And for those interested in unprojection, the basic reference with lots of ideas and philosophy and computations and everything is this article by Miles Reed, which you can find from his webpage. Thank you for all for your attention.